So if I have a function like this, where the city function is x, fx is 1 when x is equal to 2, not equal to 1, fx is 0. What does this mean? This means that this is the y value. This means that f of x is equal to 1 and f of x is equal to 0. Means that this is the y value, this is the x value. So when f of x approaches whatever value, the answer is 1. When f of x approaches whatever value, the answer is 0. Well, in this case, x, they give me the x value, they say the x is 2. So this 2 goes here, this 2 goes here. This for 1 when x is not equal to 2. So this 2 goes here, x is equal to 2. So if you had to plot this on a graph, I'll plot this on a graph now. If you have to plot this on a graph, you'd say when fx is equal to 1, x is not equal to 2. So at 2, x is not equal to 2. So the value is undefined here. It's not equal to, but the the y value is 1. So if x, so that means the graph would go this, the line would go this way. Because it's at x1 values, y is equal to x, so it's have a straight line. It's not that equation. The second one, when fx is equal to 0, fx is equal to 0, x, this value here, 2 is equal to 2. So when fx is equal to 0, that means 0 here, x is equal to 2, so that means it's a closed circle. So you have a point there. So say here now, let's say find the limit as x approaches 2. So what is the limit as x approaches 2? So find the limit as x approaches 2. So you look at the graph. What is the limit when x approaches 2? Well, always remember that a limit has values that come in from both sides. Means that the limit means it's getting closer to a point. So here it's getting closer to a point on this graph. Here it's getting closer to a point on this graph. It's getting closer and closer to 1. You can see it from the graph. This is getting closer to 1. Now, a limit. This is not a limit. This can't form a limit because a limit is something that gets closer to a point. This can't get closer to any point because there's no line here. It's just a point. So you can't take a limit of a point. So the limit would be only here only. You would ignore this. This doesn't matter. You can't find a limit of a point because you can't come in from any side. There's no line there. There's no line to tell you, well, you're coming from the right, you're coming from the left hand side. So 0. So the limit as x approaches 2 would be this point, and these two things coming from this side. This is equal to 2. Because this is 0. This line here is 0. There's no line here, there's 0. So when x approaches 2, the limit is 1. It gets closer and closer to 1. So the limit would be, from the graph you can tell, is 1. You also try to come in from one side to the next. For example, if you have a graph like this, what is the limit of this graph here? There is no limit because the graph is coming in from this side, but it's not getting closer. It's not getting closer to a point. So there is no limit. We'll talk about that later. Where there is no limits. So let's say I find the limit as x approaches 0 for the function x over x. If you would plot this on a graph, the limit of x this will give you like point where 1 gives you 1. For example, if you plot this point, 1 over 2 will be equal to 1. 10 over 10 is equal to 1. 20 over 20 is equal to 1. Minus 0, minus 0.0004 by minus 0.00004 is equal to 1. Point versus minus of 0.000006 0.00006 negative 1 equal to 1. 0.2787167.2787167. The answer is equal to 1. So any number you plot at the point, you get 1 for the y value so far. Any number that you plot, any number that you plot, you get 1 for the answer. So you always get 1. So you get a line like this on the graph. Now when x approaches 0, it will be 0 over 0, which is undefined, undetermined. So here will be open signal. Now we plot negative numbers. Now the value is positive and negative. So again 1, negative 1. So you get negative 1, negative 1, negative 1. So 1, you get negative 1, and so then you get negative 1. Negative 1 because this means that 1 is both 1 and 1. So you get values on this side as well, which is 1. Here it's undefined, undetermined. So if you look at the graph now, and look at the point in the graph, you see that the graph is getting closer and closer from the right hand side, and from the left hand side getting closer and closer to, it's not actually getting closer to anything, it's staying at 1. If you plot any value into the function, if you plot 0.004 over 0.004, you get 1. It's not getting closer, it's not even moving, all the values remain the same. No matter how many numbers you plot, if you plot 0.00001 divided by 0.00000, you still get 1. So you're not getting closer to anything as you plot values. You're not getting closer to anything. So that means that you're not getting closer to, no matter how much numbers you plug into this equation, you're not getting closer to a point. Function and the limit is a point, so that means there is no limit. So there is no limit. So for example 4, there is no limits. So let's say you have the function. Find the limit as x approaches 0 of the function 1 over x squared. What would you get? So let's plot, so you have the limit x equal to, let's plot these values into this, let's plot these numbers into this function and see what values we get. So when you plot that, when you plot these values into the function, you get these points here. So I'm going to graph these functions. So I'm going to graph negative 4. So when x is negative 4, y is very small. Look at about this. Very, very small. When x is negative 1, y is 1100. So y is a little bigger. Next is 2, y is 2.5. 0.25. So this is 1, 2, 3. Y is a little bigger than this value here. It's not 1, y is 1, so it goes up to 1. When you get to 0, it's undefined. Undefined as 0. So when you plot positive 1, now you get 1. When you plot 2, you get 2.5. 3 starts to go back down. 4 starts to go back down. So it's undefined here, but if you continue to plot, so you plot points like this. However, if you continue to plot a very small point, like 0.111, the value of this would just keep going up. For example, if you plot 1 over 0.0000004 squared, the answer would be 6,200. 5, 0, 1, 2, 3, 4, 3, 1, 2, 3, 4, 5, 6. So that means that if you plot the point 0.0000000000, you will get a value that is so high it would go up to 6,205 million. So the graph would come. The smaller you plot the point, the graph will just continue to go up and up. On this side as well, the graph will continue to go up and up. So that means at this point here, there is no limit. The graph at 0, the limit at x equals 0, there is no limit. The graph is getting bigger and bigger and bigger, higher and higher as you plot smaller and smaller points. So there's an example already. And f, right like this, limit x approaches 0 for is no limit. Right, so if we plot these points into the graph, you would plot, if you say, let's say pick points at random, -4 to +4, you plot these points, you get these points. You plot it on the graph, you get something like this. You get something coming in. But what happens at this point? Does your graph have on? If no, you plot really small points. So you plot 0.000004. That would be this small point here, and see what happens. When you plot those points, the y value is 625 million. So it means when this is 0.000004 squared, this is 6 all the way up here, 6,225,000. So the graph would continue to go up and up, so there is no limit on both sides. The graph just continue going up and up. So I'm going to do example 5, oscillating behavior. So let's say you have a graph. Let's say you have a function where you find the limit as x approaches 0 for the function. Sine is equal to 1 over x. For this function, find the limit as x approaches 0 for the sine function 1 over x. Right? If you were to plot this on a graph, you will actually get something like this. For the first couple values, from -1 and +1, you would get ordinary values. Like the values would come in up and down. You get as a function, so you get up and down function. As you come from this side, you get up and up. But in a sine function, what strangely happens is that as you get closer and closer to 0, the graph starts to go random. As you get closer and closer to 0, you just get this random up and down. The graph is moving so fast that you can't take a value. The graph is just moving up and up and up and down, and then you get to this, and then eventually starts to work normal. So the graph in a sine function, graph will go normal until it gets to this point, where it would just keep moving up and up and up and up and up and up and down. So at this point you can't get value. The value is, there's no limit at this point, no limit. Right? If you were to plot points into the graph, if you plot 1, what's the limit when x approaches? What's the limit as x approaches 1? You'd actually get a value of 1. But if you plot a point, what's the limit? So for this one is where, what's the limit as x approaches 1 on this graph? It would be, you will get a value, you might get a value of 1. But if you plot a graph as for the function, for the sine function, what's the limit as x approaches, let's say 0.0005? the answer would be no limit. So really, really small values, there is no limit. Common type of behavior associated with non-existence of limits as x approaches a different number from the right side of C. It approaches from the left side. Increase or decrease the top bound as x approaches. Oscillates between two fixed values of x. There are many other interesting functions. So this is an interesting one where at this point there is no limit. That's another example. So to recap, number one, we found limits by looking at the graph and the points can using the arrows to show that the graph is getting closer to this number. We found limit that's undefined by using a table to show if it's getting closer to any number. This case is getting closer. This is proved that getting closer to 4 on this side, so it's 4 here. Now we did limits where there is no limit when the point remains the same. It's getting close at 0. It's no connection, so there is no limit. We did limits where there is no limit, where the graph just keeps getting, as it gets closer to 0, it's just keep going. The y value just getting bigger and bigger, where there's no limit. We found limits where we've used a sine function where at a certain point, as it gets closer and closer to 0, there is no limit.